All right, statistics. This will be our last section for chapter 6. We got to start thinking about a review and a test. Some of the quizzes have not gone that well, so you guys got to get some focus here um, and make sure that we're on top of this. All right. I'm going to go backwards, and I'm going to say that we're going to fill in the bottom on section 6.6 day 1, like these directions on how to get all those dots from yesterday. We're going to fill this in after we take a look at something here. All right, for our last activity, we used a population that was skewed to the right with outliers. There's a picture, excuse me, of our original population. When you took a sample of just size 3 and started taking averages, I know you can't see this very well, but it's on your notes. It's kind of starting to cluster up here. There's still an outlier there, but if that came up in the sample, then yeah, it would be an outlier. But look, this is really starting to cluster up instead of being so skewed. And here it's a peak, and then it goes off to the right. Where here it leads up to a peak before it slightly goes off to the right. Then when n is equal to 10, I mean, I don't even think I see an outlier, and everything's really starting to group together here, but it's still kind of splotchy. When you get to n equals 20, it's starting to be one group, and then when n is 30, there are no outliers, and this thing is starting to look like a normal curve, right? That's what happens when I'm taking averages as the sample size gets bigger. Okay, so I'm going to go back to section 6.6 day 1. I'm going to fill this in. The central limit theorem goes like this. When turning a sample into an average, if n is greater than or equal to 30, if your sample size is 30 or bigger, regardless of the population's shape, the sampling distribution of x bar will definitely be approximately normal. Okay, so you guys had a normal condition for p hat and x that went if n and p and n times q are both bigger than 10, it's normal. Well, I don't have a p or a q here, so what we're finding out in these pictures is that when n gets big enough, it stops being skewed and it becomes normal. And so that's the number we're going to give. We're just going to put a straight up number on it. If n is greater than 30, the sampling distribution is approximately normal. Okay, so now we're done with section 6.6 day 1. Here we go with section 6.6 day 2. The center of this activity, it didn't change, and the spread definitely decreased. Like, look, the center is somewhere around here. Center, 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 center. It didn't move. The spread changed and the shape changed. But the topic for today is the fact that the shape changed from skewed to approximately normal. So we're filling in our last thing from the 3 sampling distributions and the center and the spread and the shape. All right, I'm going to go on to page 2 here. And we're going to actually put in the notes of the central limit theorem. I just kind of said what it was on the other page. But if you draw an SRS from any population with a mean mu and a standard deviation sigma, no matter what shape the original population is, if the sample size is large enough and you're taking averages from your sample, the sampling distribution of the sample mean, which means x bar, will be approximately normal. As long as n gets to be big enough. And what's the number we decide on? 30. It's just a naturally occurring thing that once you hit 30 and you're taking averages from your sample, if your sample size is 30 or bigger, the sampling distribution will definitely be approximately normal. All right, so the normal condition, I want to put in your notes for x bar here. The normal condition for x bar. To see if the sampling distribution will be approximately normal. Number 1, if the population is close to being normal, or if we know that it actually is a normal distribution, the sampling distribution will be normal regardless of how small the sample size is. Thing number 2, and this is for today, this is the central limit theorem that you're here to learn in section 6.6. If the population is not normal, but n is greater than or equal to 30, the central limit theorem tells us that the sampling distribution will be approximately normal. So that if I ask you a probability question, you can use a normal CDF to answer it. Example, for the population of high school students at a certain high school. The population of high school students at a certain high school. The number of texts sent every day has a mean of 45 texts. Get off your phone, people. and a standard deviation of 35. And it is definitely skewed right. You know there are some students who just never stop texting, and there are a lot of students who don't text very much at all. If you take an SRS of size n equals 100 from that school, now give the mean and the standard deviation and the shape. We are finally getting enough pieces to put all of this stuff together. The mean, so it's mu with the subscript x bar there, would be the population mean of 45. The standard deviation, sigma of little x bar, that one would go 35 over the square root of 100. And that ends up being 3.5. You guys, look how much smaller that standard deviation is than the OG over here. 35 is a population standard deviation, but our sampling distribution is just a tiny little 3.5 because of that large sample size. The shape is definitely approximately normal. I was told the population is skewed, but once I take this sample and the sample size is 100, the sampling distribution, this is what I'm talking about, not the population, the sampling distribution is approximately normal because n is greater than or equal to 30 by the central limit theorem. All right, there's a book example on page 442. Had to go and grab my Libro. On page 442, keeping it cool. The author's so funny, keeping it cool. It's got to be a temperature thing. This is a dad joke. This is definitely a dad joke. It's about a temperature thing. Keeping things cool. Let's read on page 442 what they're getting after. Your company has a contract to perform preventative maintenance on thousands of air conditioning units. Keeping it cool. You get what they did there? That's a dad in yellow pants right there looking stupid. Anyway, based on service records from the past year, the time that a technician requires to complete this work is skewed to the right, so the population is skewed. There's a mean of 1 hour and a standard deviation of 1.5. As a promotion, your company will provide service to a random sample of 70 air conditioning units for free, n equals 70, bigger than 30. So even though the population is skewed, once I start taking averages, the sampling distribution won't be as long as the sample size is bigger than 30, and it is. You plan to budget an average of 1.1 hours per technician to complete the work. Will this be enough time? So that's going to be a probability question. I've got a mean of 1. I'm saying what's the probability it'll be over 1.1. We're going to use a normal curve to answer that for sure. 1, what's the shape? Well, we can already answer that. It's normal. It's approximately normal, I should say, by the central limit theorem. Calculate the probability that the x bar average is bigger than 1.5. Well, we got to draw a normal curve and get standard deviations. We got a lot of stuff. Based on your answer to the previous problem, did the company budget enough time? We'll answer that in a sec. Okay, so the shape is approximately normal because n is greater than or equal to 30 by the central limit theorem. N was equal to 70 in this problem. Number 2, the question was calculate the probability that the average is bigger than 1.1 hours. So here's what I want you to do. Draw a little normal curve over here. Every time you do a normal probability problem, you better draw a normal curve. The mean is 1, and we're looking for 1.1 or bigger, so that's my shaded area, right? Well, the mean of x bar is equal to 1. The standard deviation, I need to put that in my calculator, is going to be the population standard deviation 1.5 divided by the square root of 70. And so I put that in my calculator. Let me get my calculator over here. I go 1.5 divided by the square root of 70. My standard deviation is 0.1793. Okay, so here we go. They ask, what's the probability that x bar is greater than or equal to 1.1? I'm going to show my work by saying that's a normal CDF. It starts at 1.1. That's the left side of the shaded area. It goes on to a giant number, so I'll put 1,000, with a mean of 1 and my standard deviation of 0.1793. So I'm going to go to my calculator and put that in there. I hit second and variables, and I get to the normal CDF part. The lower is 1.1, the upper is 1,000, the mean is 1, and the standard deviation is 0.1793. I hit enter and I get a probability. I pasted, so I got to hit enter once again. It's 0.2885. 0.2885. That's the probability that when the mean is 1, I take an average of 70 different times where technicians went out and worked. I keep track of their time. I take an average of all 70 of those. The probability that it's bigger than 1.1 hour is 0.2885. The last question was, based on your answer to the previous problem, did the company budget enough time? I'm going to say no, because there's almost a 30% chance that the average is 1.1 hours or more. 30% is way too risky. We want that number to be under 5% so that we're okay, right? 30%. There's a 30% chance of rain. Are you going to plan to have a wedding outside? You see what I mean? You see what I mean? Okay, let's go to the next page. So here we go. I am going to break down everything that we've learned again in this chapter. As I've said it several times, and for some of you it's not sinking in, and I don't think it's because it's too hard. I think it's because there's some effort issues here. A review of our 3 sampling distributions goes like this. The sampling distribution of X is the count of successes. How many people said yes out of 100 when I asked them? The mean for this came straight up out of the binomial setting. The mean of X is n times p. The standard deviation, sigma of X, is the square root of n times p times q. The shape of that sampling distribution will be approximately normal if n times p is greater than or equal to 10 and n times q is greater than or equal to 10. You guys, if this shows up on the test, you got to show the calculations. Don't just tell me that NP is greater than 10. Actually show me that 100 times 0.45 is equal to 45 and that's bigger than 10. Don't lazy your way out of that. Okay, that's the sampling distribution for X. That's when I'm just counting successes. The second one is the sampling distribution for P hat. That is not the count, it's the proportion of successes out of a sample size. So I've got a mean of P hats that doesn't go n times P, it's just P, the population proportion. And the standard deviation of P hats ended up being the square root of P times Q over N. We saw that last week. The shape for this is also approximately normal if I know that n times P and n times Q are greater than 10. So I'm going to give you the same lecture. Don't just write n times P is greater than 10. Show me numbers that it actually worked out. So I'm going to put a P hat in the margin because that's the sampling distribution for the statistic P hat. The third one is the sampling distribution of X bar, the mean of the sample, the average of the sample. All right, the mean of little x bar is the population mean mu. The standard deviation of little x bar is the population standard deviation over the square root of n. The shape is definitely normal. It's exactly normal if the population is normal. If I know the population is normal and I take samples and I take averages, I'm definitely getting a normal sampling distribution. Or I can say it's approximately normal if n is greater than or equal to 30 by the central limit theorem. If I don't know the population is normal, I can still say x bar is normal when n is greater than 30. Okay, so here is a, you know what? This is going to be your homework tonight, I think. This is what I'm going to do. We're going to do this for homework. Here's an example from a sample count. If the population proportion is 10%, that's the proportion of people who drive red cars, and I take an SRS of 120 high school students, find the mean, the standard, and the shape of the sampling distribution for X, the count. Oops, I didn't put an X bar here for this third one. Sorry, put an X bar there. So I'm looking at this information up here. Then I want you to find the probability that the amount of students with red cars is, probability is X is less than 9. I want you to find that. So I want you to find the mean of X and the standard deviation of X. I want you to show the work to say why the shape is approximately normal. Then I want you to go and find the probability that x is less than 9. You cannot do this problem and get credit from me without drawing a normal curve and putting your mean where it goes and shading and using a normal CDF. Okay, that's homework problem number 1. I'm going to turn the page. Your last page of notes today. This will be homework problem number 2 for you today. Okay, sample proportion. If P equals 0.19 is the proportion of people who drive black cars, and I take an SRS of 75 high school students, brats, find the mean, standard deviation, and shape of the sampling distribution for, not x this time, P hat, the proportion of students with black cars. Then find the probability that the proportion of students with black cars in our sample goes like this. Probability that P hat is greater than 0.25. Now, when you're using normal curves, it doesn't matter if it says greater than or equal to. They both mean the same thing because it's a continuous random variable. Okay? You're going to find the mean, so the mean of P hat. Use your formula. You're going to find a standard deviation, so the standard deviation of P hat. Then you're going to show your work to talk about whether or not it's approximately normal. And then over here, I want you to actually find the probability that P hat is greater than 0.25. All right? You're going to want to draw a normal curve, and you're going to put the mean of the P hats right in the middle. I'll do this one for you because there's literally no work to do. And then you're going to find 0.25 is up here, and you're looking for greater than 0.25, so you will shade that in and use a normal CDF. Look, I did half of a problem for you. Then the last problem for homework. You have 3 problems for homework. If the average time it takes for Keeneland High School students to drive home is mu equals 14 minutes, with a standard deviation of sigma equals 7 minutes. A lot of people live closer, and there are definitely people that live longer than 14 minutes. The shape is skewed right, because there are definitely some people driving a lot longer than 14 minutes to get to school. Some of the drives are longer. If we take an SRS of 45 Keeneland High School students and ask how long it takes to drive home, find the mean, standard deviation, shape of the sampling distribution of x bar. So I would get 45 times in minutes, and I would find the average of them. Find the probability that the drive time, x bar, is less than 10 minutes. Find the probability that I take a sample of 45 kids, and instead of getting an average near 14, I get something less than 10. All right, so I want you to find the mean of the x bars. You know how to do that. You have a formula for it. I want you to find the sigma of x bars. I want you to talk about the shape and why it is or is not normal. And then I want you to do the work and find the probability that x bar is less than 10 minutes. And of course, on this line, on all 3 of these, I want this to be a normal CDF, and then you got to put your 4 numbers in there, and then you get your answer, right? So this one will be a normal CDF, and put all your numbers in there, and then put your answer there. Now, you can cross that off and not give an answer if you find that the shape is not approximately normal. All right, so no homework out of the book, no homework on sapling. We're going to do those 3, and then in class tomorrow, we'll start doing a review, but here's something I definitely want to do. I want to have you guys have calculators in front of you and do normal CDFs and do these probability problems. So we're going to have kind of an extra practice for section, what would it be, 4, 5, and 6. And then we'll do kind of a review outline and a bigger review the day after that. All right, that's your job for today. Have a good day, everybody.